Hello, and welcome to another edition of Mr. Chappell's Chemistry Screencasts. Today, we're going to learn how to use the gas laws. There's two things that we're going to learn to do today. First, how to use the combined gas law equation. And second, how to use the ideal gas law. Now, there are a couple of things that you're going to need. You're going to need a calculator, of course. You're going to need a periodic table. And lastly, you're going to need to have the gas law constant ready to use. Now, this is a physical constant, so of course I'll always give it to you on a test or a quiz. Let's go ahead and go through three examples. Okay, here we are with our first question, and we're told a sample of gas with a volume of 2.5 liters has its temperature changed from 25 degrees Celsius to 95. What is the new volume going to be? Well, we're going from 25 degrees Celsius to 95, so we would expect that the volume is going to increase because the temperature is increasing. So let's go ahead, and the first thing we want to do is write down the equation that we're going to apply. And you'll notice that we have changing conditions here. We're starting with a low temperature, we're going to a high temperature, so this is clearly a case for the combined gas law equation. And let me get my pen tool working here, and that's going to be P1 V1 over T1 is equal to P2 V2 over T2. Now, we're not told in the problem what's happening to the pressure, so we can go ahead and assume that the pressure is being held constant, and so those terms are going to cancel out straight away. And we need to pull V2 over to one side, so let's go ahead and multiply each side by T2. And we notice that the T2's cancel. Hooray for algebra. And what I get is, flipping it around, V2 is equal to T2 V1 over T1. Okay, now I'm going to rearrange things just a little bit. I'm not actually doing any algebra here. I'm just kind of collecting terms a little bit to neaten it up. And this is what I get. So let's go ahead and plug in our numbers. And the starting volume is 2.5 liters. And the starting temperature is 25 degrees Celsius, so we're going to convert that to Kelvin, and that's 298 K, adding 273 to that, and the ending temperature is going to be 368 K. And go ahead and cancel our units, and you'll notice that the only unit that we have left standing is the liter unit, so that is the unit that we want. And we're allowed two significant figures in this problem, and so what I get is 3.9 liters. And we can also do a reality check on this. Well, the volume did indeed go up, and the temperature went up, and volume and temperature are directly proportional, so that's kind of what we would expect. Okay, here we are again, and this is a more complicated problem. In fact, this is probably as complicated as I can make these kinds of problems. And we've got changing conditions. So again, this is a case for the combined gas law equation. So we've got P1 times V1 over T1 is equal to P2 V2 over T2. And we're being asked to figure out what the new pressure is, and that's V2. So we need to get P2. So we need to get P2 off by itself. So I'm going to multiply both sides by T2 over V2. And you'll notice that the T2 cancels here, and V2 cancels here. And on one side of the equation, we have P2. So I'm going to go ahead and flip it around. And what I get is T2, P1, V1, all over V2, T2, T1, excuse me. Now I'm going to go ahead and shift these around just a little bit. Now I'm not actually doing any algebra here, I'm just kind of prettifying the equation. Okay, so our starting pressure is 3.4 atm, and our starting temperature is 298 Kelvin, taking 25 degrees and converting it to Kelvin, and our ending temperature is 279 Kelvin, and our initial volume is 3.3 liters, and our final volume is 2.4 liters. And so you'll notice that the units cancel, and the only unit left standing is atmospheres, and that's kind of what we want. And my calculator gives me, and we're allowed just two significant figures, my calculator gives me 4.4 atmospheres. And that's our final answer for this problem. Okay, here's our last one. And what confuses a lot of people is, when do I need to use the combined gas law equation, and when do I need to use the ideal gas law equation? Well, the combined gas law equation is only used for changes in conditions. You're expanding or compressing, you're raising or lowering, you're heating or cooling. Whereas with the ideal gas law equation, you just have a static system. Nothing is changing. And that's pretty much what we have here. So the first thing I want to do is write down the ideal gas law equation, and that of course is PV is equal to nRT, and I need to get volume off to one side, so I'm going to divide both sides by the pressure, and the pressure cancels on the right hand side, and all I'm left with is the volume, and I get volume is equal to nRT all over P. So what we need to do next is to plug in our values, and first bit of business is we need to figure out how many moles are in 4.5 grams of O2. So I'll go ahead and do that right now. 4.5 grams of O2, and put it all over 1, and for every 32 grams of O2 we're going to get 1 mole of O2. And 32, again, that is the molar mass of oxygen, each of the oxygens being 16 grams. And my calculator tells me that I have a total of 0.141, and that's moles of O2. Okay, now I'm ready to plug everything in. And so for my first term in, I have 0.141, that's moles of O2. And the gas law constant, of course, is 0.08206. That's liters, atmosphere. Whoops. Let's try that again. Liter, atmospheres per mole degree Kelvin, and the temperature is 298 K, and the pressure that I'm given is 0.56 atm. Now let's just stop and make sure our units are going to work out correctly. ATMs cancel, moles cancels, and last but not least, Kelvin cancels, and the only unit that we have left standing is liters. And my calculator gives me, and again, only allowed 2 sig figs in this problem, 6.1 liters of O2. And that's our final answer. And that's how you do it. This concludes our lesson.